Hello, Steve. Today's Friday, March the 14th. Or Pi Day, if you prefer. Interestingly enough, you posted a video on my wall which describes how less than special pi is, and I'm about to knock down all those things I said right now. While they made some pretty valid points, the point they're overall missing is that pi is actually quite special. What makes pi so special is how accessible it is to everybody. They mentioned pi living in a vast world of irrational and transcendental numbers, which is completely true, it's just one of many. But what they fail to mention is that pi is actually one of the few transcendental numbers that people actually know. And by that I'm referring to people in the general public. Everybody knows circles, and from knowing circles comes the understanding of what pi is. As they describe in the number file videos that you and me both love to watch, pi is one of the superstars of the math world. Pi is to the math world what Leonardo DiCaprio is to the movie world. Even if you're not that familiar with movies, you pretty much know who he is and what he's done. And pi receives the same kind of superstar treatment. To make this point clear, we're going to talk about something known as transcendental numbers. There's a certain hierarchy to numbers, and they go as the following way. You start off with your positive natural numbers. This is 1, 2, 3, 4, so on and so on. The next extension is the whole numbers, where you pretty much take all the natural numbers, you just add 0 to it. And you'll see as we go through these different extensions, all you're doing is you're adding to the previous group. The next extension is the integers, and that includes all positive and negative whole numbers, so 1, 2, 3, 0, and -1, -2, -3, so on and so forth. The next extension is the rational numbers, meaning any number that can be written as a fraction, so like 1/2, 3/2, stuff like that. And the rational numbers are just an extension because all integers are rational numbers. Numbers like 2 can be written as a fraction, 2/1, or 4/2, or 6/3, so on and so forth. And then comes the next hierarchy of numbers, irrational numbers. Now, this is the first extension that doesn't actually include the previous one, because rational numbers are not irrational numbers. By definition, irrational means that it can't be written as a fraction. And irrational numbers are given merit by incorporating numbers that we're all familiar with, like the square root of 2. There's some very nice proofs out there that the square root of 2 cannot be written as a fraction. I encourage you to look at them. They're pretty cool. So the next level up is irrational numbers. But there's another type of number that incorporates both some of the rational numbers and all rational numbers. And that's algebraic numbers. Algebraic numbers are any sort of number that can be a solution to some sort of a polynomial. For example, the square root of 2 is an algebraic number because the solution to the polynomial x squared minus 2 equals 0. And much like irrational numbers are numbers that can't be written as a fraction, the next level up is transcendental numbers, numbers that can't be written as a solution to a polynomial. And of course, transcendental numbers wouldn't be all that interesting if you couldn't prove that one of the superstars of math was a member of that group. So when mathematicians proved that one of the superstars of the math world, pi, was actually a transcendental number, it put huge merit on transcendental numbers. All of a sudden, that became a huge topic of interest. So even though pi is one of uncountably many transcendental numbers, making it sort of not that special, it's special in the sense that it actually was the reason transcendental numbers are important. If transcendental numbers were up for an Oscar, pi would be up for Best Actor in a Lead Role. Another thing the video mentions is how pi isn't that special, because there's lots of other numbers that are ratios of similar types of shapes. For example, there are ratios in triangles and squares that produce other interesting numbers. And I sort of agree with this argument, but not fully. I mean, there's lots of different triangles and lots of different quadrilaterals, but there's only one type of circle. Not only that, when you look at the ratios of right-angled triangles, it has its own branch of math, and that's known as trigonometry. But when you look deeper into trigonometry, it's all actually stemming down to circles, and that's where pi tends to keep coming in. So even with other ratios, pi ends up playing a huge role. On the lighter side of things, here are some of my favorite facts about pi. For starters, I'm pretty convinced that the reason pi is so popular is because it pretty much sounds like a tasty food dish. I'm not sure people would be as excited for Tau Day. Pi Day is just a lot more fun. By the way, tau is twice the value of pi, and a lot of people in the math world view tau as a more natural way of viewing things. And you'd celebrate Tau Day on June 28th, likely by eating twice as much pie as you would on Pi Day. Another interesting fact, a lot of people like to recite digits of pi. The Guinness World Record for reciting digits of pi is 67,890. And what's truly amazing about that is it took the guy 24 hours to do it. Also of interesting note, the number of digits he recited go in the order 67890. Another cool thing about pi is it's involved in something known as Euler's identity, which is so cool because Euler's identity is like a big blockbuster movie. It has pretty much all the superstars of math involved. Euler's identity, e to the I pi plus 1 equals 0. What's so cool about this is it involves e, I, pi, 1, and 0. Pretty much the biggest superstars you can get in math. Another interesting thing about pi is when you view it as a continued fraction. What a continued fraction is, you'd sort of get a fraction inside of a fraction inside of a fraction. It just keeps going on forever and ever. There's also a field of generalized continued fractions, and some of the ones for pi come out really nice. Take a look. This is a continued fraction, a fraction that just kind of keeps going and going and going. And the nice thing about these things is there's nice patterns that form. You can see the 1, 3, 5, 7, 9 all there, and there's also 1, 2, 2, 2, and it just keeps going with 2, so that's pretty cool. If you looked at this one, the same kind of thing's going on. You get 1, 3, 5, 7, 9, and then there's some sixes at the bottom there. What's really cool about these continued fractions is the fact that if you're to stop them at any point, you get a pretty good approximation for what pi is in terms of a decimal. According to a Doodle search I did, the number of digits of pi known is about 5 trillion. Although that number may not be accurate to this date. Which begs the question, how do we get digits of pi? Now, if you're thinking we just draw giant circles and measure the ratio between the circumference and the diameter, you'd be completely wrong. Although that can give a pretty good approximation. The answer to how do we find digits of pi lies in a field of math known as infinite series. What an infinite series is a continuous adding of a sequence over and over and over again, forever and ever. For example, 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus ... You just kind of keep going like that. So let's take a look at how it's done for pi. If you remember from high school, tangent is the ratio of the opposite side to the adjacent side in a right-angled triangle for a given angle. So for example, for a 45-degree angle, the tangent would be the ratio of the opposite to the adjacent, and that would actually be 1, because for a 45-degree angle, the opposite and adjacent sides are the same. Alternatively, 45 degrees can be viewed in radians as pi over 4, so tan of pi over 4 is 1. What arctan is actually the inverse of that, so that means that arctan of 1 is pi over 4. To figure out digits of pi, we use the arctan infinite series. We're not going to get into much detail where this infinite series comes from, but we'll just talk about that as useful for figuring out more digits of pi. Because arctan of 1 is pi over 4, if we set z equal to 1, and then we multiply both sides of the equation by 4, we would end up getting this equation. So pi is 4 over 1 minus 4 over 3 plus 4 over 5, and so on and so on. Now, the problem with this for computing digits of pi is it takes forever for it to actually converge. So to compute digits of pi faster, what you do is use known trigonometric identities. For example, this one over here. Pi over 4 equals 4 arctan 1 over 5 minus arctan of 1 over 239. So for arctan of 1 over 5 and arctan of 1 over 239, you only would need about 3 or 4 of the first terms of that infinite series for arctan we saw earlier. And using that, you can get a pretty solid approximation for pi. I encourage you to try it for yourself if you feel like you understood any of the stuff I just talked about. It's understandable if you didn't get any of the stuff I just talked about. So that's enough about pi. How about some other stuff? Actually, one more pie thing. I made a chocolate pudding pie today. I did so following a recipe in the back of an Oreo cookie crumbs box. But once again, pictures will be shown in a later video. Finally, chess time, and for the last time as well. Now, I warned you in my last video that you can't move the bishop, and you did that anyways. So let's take a look at the board before you move the bishop. And here it is after moving the bishop. My move is rook from h1 to h5, which takes out your rook. And that is checkmate. I will not gloat because chess is a game of class. Our next game will be Battleship, and as we've discussed, you'll start that off on Tuesday, so we'll get the boards ready over the weekend. So until the next time, enjoy some delicious pie. And have a happy St. Patrick's Day. Pie for now.